All right, let's keep in context what we're trying to do here, which is we have a structure that has some loads, and we've been asked to find the axial stress in a particular member. In order to get there, if this is where our starting point is, we have to perform our truss analysis to figure out what the force is in the specific member, which is this middle one in this particular case, CG. We've done that, and the internal force that's been developed is 200 kips and tension. Right? So if you turn to the next page in your notes, then here's where we're going to do the whole work. If you funnel in on the real drawing, here's our assembly that we've got. We've got two I-bars. An I-bar is a member that's got this rectangular cross-section. That's the 1.5 by 5 in this case. It comes down and then it flares out into this rounded portion, in the middle of which is a hole. And that hole is there so that a pin can go through and attach it to the rest of the assembly. And we got two of those that are resisting in this entire 200 kip force. We're worried and interested in, at this stage, not what happens down here in this detail. We'll look at that too. But right now we're just looking at what happens away from that end connection in the gross part or main part of the member where we have this 200 kips. Right? And so, in a sense, if we're pulling on that thing, we got to be concerned about, if we keep pulling, do we end up with fracture or some other kind of situation that we don't like? Right? And so we're trying to capture what the applied stress is in this particular scenario. Right? So let's take another look down below. Here's some details about this particular I-bar, some geometric details. And this is just one of them that we're showing. So we're assuming that the 200 kips total is being broken between the two parts in an even kind of way. Right? Hence, that's why there's only 100 shown in this. And then on that rectangular cross-section, we're going to turn that axial force into an average axial stress. So let's see how we're going to really do that calculation. Right? So we're going to find the axial stress in member CG. We're given that its axial force is 200 kips and tension. That's the total force. Right? So not just in one of the bar, total force. And we have two of these I-bars. So let's first find the cross-sectional area. Right? And so we'll call that total area A sub G, the G standing for gross area. Right? And so we have two of these rectangles at 1.5 inch and by 5 inch. Right? So let's see, 2 times 1.5 is 3, 3 times 5 is 15. So we have 15 square inches total for that. Right? So now let's find the axial stress. Right? And our definition of axial stress, remember that's given the symbol sigma, and sometimes it's given the lowercase symbol a for axial, that our axial stress is going to be given to us by our axial force divided by our gross area. Right? And since this is 200 kips total, and our total cross-sectional area is 15 square inches, then we want to do 200 divided by 15 equaling then 13.3, notice here, kips per square inch, which is oftentimes written also as KSI, kips per square inch. And remember that 1 kip equals 1,000 pounds. That K is similar to a kilo, as in kilonewton, kilogram, those sorts of things, because it represents 1,000. But in this case, a kip, K-I-P, right? That's not the children's breakfast cereal, but that kip is 1,000 pounds. Oh, wait a minute. Holy cow. The average axial stress is 13,300 pounds per square inch. In your typical car tire, you might have air pressure of about 35 psi. This is 3 orders of magnitude larger. These are very large values in structural materials. Right now, this is not quite all correct because it matters whether this is in tension, being pulled apart, or whether it's in compression. Another thing just to point out here, that for our answer is that of course we want to clearly mark all that stuff and have an appropriate level of significant digits, but that we didn't have to calculate it this way. We could have just done one bar over and used its axial force divided by its axial cross-sectional area. Both numbers here would have been divided by 2, so we get the same thing either way, but that's also why this is an average axial stress as opposed to what we might experience in some little micro portion of the cross-section when things are a little different than maybe our model is telling us, right? So this is an average model. We'll get into more sophisticated models at another time, usually in an advanced course, but even in this course later on, we'll actually get in the bending section to where we don't have this F over A. There's something a little bit more complex than that.